Welcome back to Earth Science. Chapter 4 was all about the structure of the Earth and the formation of the Earth. In Chapter 5, we're going to start talking about the physical substances of the Earth. And we're going to start at the very smallest substance, the atom, and we're going to move up to minerals. And minerals are going to be about the biggest we go this chapter. Next chapter will be over rocks, and then we'll start about talking about resources and mountain building and all of that good stuff. So let's jump right in. What is matter? Well, matter is anything that has mass and volume. And to describe mass, we talk about the amount of matter inside of something. They're kind of circular definitions, but they're very important. You can't have mass without having matter, and you can't have matter without having mass. Weight is the force that gravity exerts on an object. Weight is different than mass. Your weight can change based on your location. Your weight is a lot different here on Earth than on the moon, but your mass is still the same. There's still the same amount of you just weigh different. And the volume is the amount of space taken up by an object. And all of these are important terms that we're going to use pretty colloquial this chapter. So elements, all matter is composed of elements. And all of these elements are substances that cannot be broken down by ordinary chemical means. No boiling or chemical reactions will break down gold into a smaller thing. It is gold at its base core. Elements each have a name and a symbol on the periodic table. For example, gold is Au, hydrogen is H, and oxygen is O. If you see something on the periodic table like gold, where the letters are not what you'd expect them to be, you'd expect them to be G, but Au is actually from the Latin word for gold. The same is true of silver and antimony and tin, and a lot of those, and iron and copper all have their names come from Latin, so they have a different symbol on the periodic table than you'd expect. All elements are made up of atoms, and the atom is the smallest part of an element that has all of that element's properties. The structure of atoms, we have three parts. We have the proton, the neutron, and the electron. And each of these, in this helium atom here, we have the neutrons here and the protons here, and these little electrons going around the outside. Each of those has an important role that it'll play. The nucleus contains both protons and neutrons, these larger particles. The protons are positively charged and the neutrons are neutral. They have no charge. So think pro, positive, neutron, neutral. The atomic number is the number of protons in an element. So if you have more protons, you are a different element. Electrons, this third part of an atom, have a negative charge and they circle around the nucleus. And there is usually the same number of electrons as protons. So if you have an atom with 8 protons, you would expect that atom to have 8 electrons. Hydrogen is our very simplest element. It has 1 proton in the middle. It does not have a neutron all the time. Sometimes it can, and that's an isotope. We're going to talk about that. And it has 1 electron. This here does not have a neutron. This is just 1 proton and 1 electron. It is the very simplest element that exists. Helium, we've now bumped up to 2 positives and 2 neutrons and 2 electrons. The atomic number for hydrogen was 1. We had 1 proton. For helium, the atomic number is 2. We have 2 protons. Carbon has 6 protons in here. It has 6 neutrons and it has 6 electrons. And these electrons are grouped into different energy levels. There's this one closer to the nucleus and this one farther out from the nucleus. As you get more and more electrons, you have to get more and more energy levels to hold them. Each level is limited on the amount of electrons it can hold. The first can hold 2 electrons, the second can hold 8 electrons, the third can hold 18 total electrons, and so on and so forth. The periodic table is a big table that lists all the elements and groups them together on their periodicity, which is the repeating group of factors and functions that these guys have. The atomic number is the number of protons. It determines your element's names. Carbon has 6 protons. Boron has 5 protons. Beryllium has 4 protons. Isotopes are the same element with the same number of protons, but they have a different number of neutrons. So when we talk about like uranium-235 versus uranium-238, they both have 92 protons, but they have a differing number of neutrons. You can actually find out how many neutrons something has by looking at the mass number. The mass number is the sum of the weight of all protons and neutrons in an atom. These are added all together. Protons and neutrons are worth 1 AMU. If you take chemistry with me, you'll learn what AMU means. It's atomic mass unit. They're equal the same. They're both equal to 1. So if you have a oxygen atom that weighs about 16 mass units but is 8 protons, you can tell me that their 16 minus 8 would be 8 neutrons. So you could figure out how many neutrons are inside that oxygen. On the periodic table, you'll have this periodic mass number. Inside of nature, there's naturally occurring isotopes with these different number of neutrons. They all have a different mass number. To figure out what number to put on the periodic table, they take all of them, all the atoms on the Earth, or that we think they are, and the ratio that they are, and they figure out percentage-wise how much weight goes into that, and that's what the periodic mass number comes down to. Most of our substances aren't pure elements. We have this bonding that happens of our atoms. They are a mix of elements, like water is a mix of two elements, hydrogen and oxygen. A compound is any substance that forms from two or more atoms that are chemically combined. And there's 3 types of bonding that can occur. There's covalent, there's ionic, and there's metallic bonds. In covalent bonds, these are when atoms share electrons. These electrons are trapped in between the two of them. They're kind of sharing them more or less equally. A molecule is when 2 or more atoms are covalently bonded. A molecule can also be a compound, but a compound isn't always a molecule. Some elements naturally exist covalently bonded to themselves, things like nitrogen and oxygen. You'll find N2 and O2 very commonly in nature. We breathe O2. It's a very important part of our atmosphere. Ionic bonds, if an atom gains an extra electron, the electrons the negatively charged particles, the atom itself becomes negatively charged. If it loses an electron, it loses a negative charge, it now becomes positively charged. Anytime we have a charged atom, we call it an ion. These opposites attract. The positively charged ions, the ones that have lost an electron, and the negatively charged ones, the ones that have gained electrons, are attracted to each other. This is how we form salt. Sodium wants to lose an electron, and chlorine wants to take an electron to fill its outer shell. So as the chloride takes an electron, it becomes negatively charged and is now attracted to the now positively charged sodium ion. And that's how we get table salt. Metals are a little special. A metal is any element that loses electrons easily to form positive ions. Things like aluminum, sodium, potassium, gold, and silver will all readily lose their electrons. We do not see ionic bonds forming between metals. Instead, we'll see these metallic bonds. There are nonmetals on the periodic table. These are the ones on the right-hand side of the periodic table. They're ones that easily gain electrons to form ionic bonds. Things like nitrogen, oxygen, fluorine. And like I said, they're located on the right-hand side of the periodic table. Metallic bonds form specifically between metals, and all the atoms are positively charged. Now, instead of electrons, binding to other atoms, they instead travel in a sea of electrons around the outside of this positively charged mass. So instead of normally where an electron would go around one nucleus, these metallic electrons are going around all of the nuclei. Compounds and mixtures. Compounds can have completely different properties than the elements that make them up. Take, for example, salt. It's made out of sodium, which is highly explosive in water and air, and chlorine, which is a deadly gas, and you mix them together and you get harmless table salt that we can readily consume and enjoy. Water, both hydrogen and oxygen will exist in gaseous forms unless they're bound together to form water, where they form a liquid. And hydrogen peroxide. Hydrogen peroxide, the formula for water is H2O. So we think, hydrogen and oxygen, good for us. Hydrogen peroxide is just H2O2. Just that one extra oxygen now makes it toxic for our cells. So what they're made of does not make up their properties. It's how those actually combine together to form their properties. So compounds have different properties than the elements that form them up. In mixtures, individual compounds keep their own properties. For example, in salt water, we can separate salt water out without chemical means. We can boil off the water and get the salt. We can precipitate the salt out using a solution. Now, compounds, on the other hand, cannot be separated by physical means, so only mixtures can be separated by physical means. So, when we start talking about minerals, we have to ask ourselves, what is a mineral? And a mineral has 5 characteristics that make it a mineral. It has to occur naturally. It has to be a solid. It has to have a definite chemical composition. Its atoms have to be arranged in an orderly pattern, usually crystalline. And it has to be inorganic, meaning that it was never alive. So things like coal or oil are not minerals. They were alive at one point. They cannot be a mineral. Mineral has to be inorganic, never alive. There are around 4,000 known minerals. Some examples are quartz and gold and diamond. Example of non-minerals, things like coal and water. Water, even though it's inorganic and wasn't ever formed from a living thing, it doesn't exist as a solid. Ice does, but ice isn't a mineral either, because it can switch between a liquid and a solid very easily. So Earth's crust, there's 8 minerals that make up 98.5% of the Earth's crust. If you're trying to remember that number, 98.5, just remember it's 1 point less than body temperature. And these minerals include oxygen and silicon and aluminum, iron, calcium, sodium, potassium, and magnesium. So compounds, these are materials formed of several elements. For example, quartz is a compound of silicon and oxygen, and galena is a compound of lead and sulfur. So they're made up of different atoms that make up a different constitution for them. Our native elements, these are ones that consist of single elements, things like silver, copper, sulfur, or even diamond, which is just carbon. Mixtures of compounds and native elements equals rocks, and most of what we see in our day-to-day life are rocks. Mineral formation. Many minerals form from molten rock, which we call magma. In magma, atoms and molecules can move freely around like a liquid. They can move past each other, kind of sliding past each other. As they cool, the atoms and minerals form bonds to each other, either metallic or ionic bonds most of the time, and this forms armed bonds for minerals. The types of minerals you get depends on how the magma cools. The rate at which it cools decides how big these mineral grains form. Things that cool slowly can get much bigger. Things that cool very quickly turn into very, very small crystalline structures, very, very small shapes. So like we were kind of alluding to in the last slide, there's a timeline for mineral production. It can happen really fast or really slow. They can form as water-containing molecules slowly evaporates and leaves like the salt behind. As water evaporates, atoms bond together, and this is how we get halite, which is a mineral formed from salt left over from evaporation. As it slowly evaporates away, it leaves behind this nice crystal of halite. We can transform minerals into different minerals, and there's 3 ways that we can do this. We can do it via heat, via pressure, or via chemical action, or any combination or mixing and matching of all 3. The structure of minerals. All minerals have a crystalline shape, which means that they have a regularly, orderly arrangement of atoms. A crystal is a geometric, regular solid with smooth surfaces. And the faces of a crystal are the smooth surfaces of the crystal. They're the ones that kind of reflect the light back out. For example, we have salt crystal, which is halite. Each sodium is bonded to 6 chlorines, and each chlorine is bonded to 6 sodium. This pattern is repeated, and as a result, halite has a very cubic shape. As you can see by this picture here, it forms a very nice cube. The purple is the sodium, the green is the chlorine. Nice bonds forming here. And all minerals have a unique shape, unique to them. Halite has this nice cubic shape. Quartz, on the other hand, has a very long 6-sided crystal. They look very different from each other. All right, so the angle a crystal's face meets is characteristic for each type of mineral and can be used for identification. For example, halite, the one we've been talking about of salt, its faces meet at a nice 90-degree angle. And quartz, to get that nice six-sided crystal, they meet at 120-degree angles. Not all crystals have faces. If there's not enough space when the crystal is forming, there's not enough room for that face to fully form. This mineral will still be crystalline, however, but its faces are not visible. They're microscopic crystals. There's 6 basic types of crystal shapes, and then off of that, most crystals have a little bit unique kind of angle on them, or they have several different crystal shapes inside of one mineral. Makes them a little bit different from each other. On each mineral, we're going to have an axis, which are these imaginary lines that run through crystal shapes. These crystallographic axes are used to distinguish between our different crystal shapes, and each of these axes must pass through the center of a crystal. Not going to be offset. It has to go right through the middle and kind of split it in half. The silicates are our most common minerals. Silicon and oxygen, if you remember from our list a couple slides back, are the 2 most abundant elements in the Earth's crust. And so most minerals contain these elements. So silicates are our most common mineral. All silicates have the silica tetrahedron. This is 4 oxygen atoms packed around a silicon atom in the middle. This shape is a tetrahedron. And all silicates are composed of this formation. The thing that makes silicates different from one another is their orientation changes. Cleavage is the tendency of a mineral to split along different planes, and this corresponds to weak bonds inside of a mineral. Some minerals like quartz don't have any cleavage. They're very strong minerals. They're very good at, scratching things. They're not so good at being broken down. Speaking of hardness of a mineral, the hardness of a mineral is determined by the arrangement of its ions, its atoms, or its molecules. When carbon is arranged in a tetrahedral network, the result is diamond, which is very, very strong, very, very hard. When it is arranged in sheets, it forms graphite, which is the soft material that you might find in a pencil. Same material, but very, very different levels of hardness, very different properties based on how they're arranged. When we're going to identify minerals, this is kind of an introduction to mineralogy, which is the study of minerals and their properties. Many minerals can be identified and classified by inspecting both their visual and physical properties. Our rock-forming minerals is a group largely composed of silicates, and rocks usually consist of several different types of minerals, making identification of rocks much more difficult than identification of minerals. So we usually use physical properties to distinguish minerals, not so much when we're looking at rocks. We use some more broad characteristics when you're looking at identification of rocks. So our first physical characteristic is color. It is the easiest observable mineral property. Some of them have very unique colors, like cinnabar, which is an ore of mercury, is very red, and malachite, which is an ore of copper, is very green. On the left here is some nice cinnabar. It's very red, and malachite, on the other hand, over here is very green. But color isn't always our best property to use. There's some big disadvantages for using color. And in fact, it's our least useful characteristic. Minerals can have several colors. They can look, both of these minerals are red. Impurities can turn colorless minerals into colored minerals. For example, if you add iron to clear or white quartz, it turns purple, changes the whole color of the mineral, even though it's still quartz. So on the left-hand side here is some nice pure white quartz, and on the right is this kind of purple quartz that has a whole bunch of iron mixed into it. Luster is the way a mineral shines in light. It can be described as having either a metallic luster or a non-metallic luster. Metallic lusters shine like polished metals. They look very silvery or coppery or golden. Non-metallic lusters, there's lots of different non-metallic lusters. There's vitreous luster, which is a glass-like kind of shiny appearance. There's a pearly luster, where it looks like a polished shell or like you would see a button on a shirt. There's adamantine luster, which is brilliant. It's the shiny luster we see on diamonds. And there's other examples like greasy or oily or dull or earthy lusters, and all of these are examples of non-metallic lusters. Using the crystal shape, we can help identify a mineral. It's not always useful if you don't have like really nice crystal faces forming. And usually out in nature, just finding the perfect crystal face is pretty difficult. It's a pretty difficult task. It's very rare for these minerals to get just the perfect formation. When we test mineral samples, we're going to use hand samples. These are samples large enough that you can hold in your hand, that you can easily observe. Some minerals can't be observed only using one observation. You're going to have to use more than one trait to determine these minerals. You'll have to use a mix of cleavage and color and hardness. Some physical tests we can use is, number one, we have streak, which is the color of a mineral's powder. This is obtained by rubbing the mineral on an unglazed white tile called a streak plate. In many cases, the streak will not be the same color as the mineral. But streak will always be the same color for the same mineral. So cinnabar here will always have this kind of reddish brown streak. No matter what color cinnabar you have, the color of the mineral, it will have the same color streak. Same thing with pyrite. It will have this greenish, blackish streak there. You have to be careful when using a streak plate because some minerals are very soft and you'll actually end up like just scratching them against the streak plate and it's not actually streaking them. So you want to just be gentle and just very gently rub that rock across the streak plate. Second is cleavage. And like we talked earlier, cleavage is the set of weak bonds in a mineral. This means that that mineral, that chunk of that hand sample will look like it's going to split very easily along a certain edge. Some examples you're going to see are mica, which split very easily into thin sheets like paper, and feldspar, which really splits in two directions. So it looks like it has two weak spots inside of this mineral sample. Fractures are breaks in a mineral that don't happen along the cleavage surface. There are several different types of fractures. This is like how this rock is going to break. There's things like conchoidal fractures, which are smooth and they're kind of curved like a clamshell. There's a splintery fracture, which leaves a jagged edge, like you would expect on like an arrowhead. And then there's uneven or irregular, which leaves a generally rough surface that doesn't really look like a conchoidal or a splintery fracture. The fourth is hardness, and this is the resistance of a mineral to being scratched. Of all the minerals, diamond is the hardest. It will scratch any other mineral, and talc is the softest, meaning that any other mineral will scratch talc. Mohs scale for hardness was developed by mineralogist Friedrich Mohs, and it is a numerical scale that is used to express mineral hardness. On this scale, Mohs took 10 really well-known minerals and assigned them numbers 1 through 10, talc being number 1 and diamond being number 10. The only downside for Mohs hardness is the increase from 1 to 2 and 2 to 3 and 4 to 5 and 9 to 10 isn't incremental, it's not uniform. So while 1 and 2 are very close together, 9 and 10 are very far apart. Our last kind of regular property is going to be specific gravity, and this is the ratio of a mineral's mass to the mass of an equal volume of water. This tells you how dense this mineral is compared to water. The denser the material, the more water it will displace, and the quicker it will sink in a solution of water. There are some special properties of minerals that aren't found in every mineral. Things like double refraction, which causes a single object to appear as two when viewed through a mineral. There's fluorescence, which allows a mineral to glow when viewed under ultraviolet light, such as blue UV light. Halite has a salty taste. And some minerals are magnetic, meaning they are attracted to a magnet. And we won't see any of these, but there are some radioactive minerals that give off subatomic particles, and these are the ones that can be detected by a Geiger counter. They're radioactive. So we're going to briefly just discuss the different groups and families of minerals. Minerals are, we're going to have first the group, which is the large category, and then inside of the group we'll have families, which are the smaller categories. 90% of our minerals are going to be silicates. So they're going to have silicon, they're going to have oxygen, and they're going to have one or more metallic elements kind of mixed around in there. For all of these, they're going to have a silica tetrahedron as their basic building block, and then they're classified differently by how their tetrahedrons link together. Quartz is our first family in here. They're made of tightly bound silica tetrahedrons. The chemical formula for quartz is silicon dioxide, or SiO2. And these guys have glassy or greasy lusters. Pure quartz, that is just silicon dioxide, is going to be white or colorless. All of them are going to have conchoidal or irregular fractures, and most will have a hardness of around 7 on Mohs hardness scale. It is the hardest of our quote-unquote common minerals that you can come into contact with just about anywhere on the planet. Some uses for quartz are they're used in watches, inside of prisms, they're used to make glass and paints. Crystal quartz can often be worn as a cheaper alternative for jewelry. And we can find quartz in granite and sand. It is our second most common silicate. Our first most common is the feldspar family, and this makes up 60% of Earth's crust, a large majority of the rocks that we see. And all feldspars have 3 common features. They have a hardness of 6, they have a pearly luster, and they have 2 directions of cleavage where they have those weak bonds inside of those rocks. In the structure of these guys, they're going to have atomic atoms are going to replace some of the silicon ones. So you're going to have some aluminum oxygen tetrahedrons, which causes an electrical charge inside of these. Things like potassium, sodium, or calcium are going to be attracted to this charge. And the feldspars are going to be further split into 2 different groups. The first is orthoclase, which are light-colored pink or salmon. And they have 2 cleavage structures here meeting at 90-degree angles. And we commonly see these in granite. Our second type is going to be plagioclase, which range in color from white to gray. And their cleavage surfaces are going to meet at less than 90 degrees, or an acute angle. One of their cleavage surfaces is often marked with fine parallel lines called striations. You can see them running up and down in the sample here. And feldspars are used to make glass and ceramics. Our next family is pyroxene, so this is still inside of the silicate group. And they have cleavage surfaces at 90-degree angles. The most common is augite. And every mineral in this family is a ferromagnesium silicate. And ferro is the word we use for iron and magnesium. So all of these are going to contain a mixture of both iron and magnesium. This means that they'll be very dark in color, and they'll have a hardness in between 5 and 6. Mica is another family of our silicates. They're very soft. They have a hardness of around 2.5 to 3. They form perfect cleavage in only one direction. As you can see from the sample here, there's some thin sheets that you could look like you could peel off there. Muscovite is very white mica. It's silvery white. Biotite is a very dark mica. It's a dark brown or black. And these are used in paints and plastics and roofing. Amphibole is another family of our silicates. These are very complex and they form long, needle-like crystals. Hornblende is our most common. This is what's in this picture here. It can be shiny dark green, brown, or black. It is a 5 to 6 on the Mohs hardness scale, and it has 2 cleavages that meet at oblique angles. Our olivine family, these are olive green in color. They have a hardness of 6.5 and have a glassy shell-like fracture. We find olivine, surprisingly enough, in some meteorites. So it's kind of one of those cool ones that we see in extraterrestrial rocks. Kaolinite is an aluminum silicate formed from the weathering of feldspars. It's white in color and is very soft. It only has a Mohs hardness of 2. And it is perfect cleavage in one direction. It is sometimes called china clay because it is commonly used in ceramics. Now our next group, so big category, is the carbonates. And they are made of mostly negatively charged carbonate ions, which are bonded to positively charged metal ions. Remember we talked that metals are very commonly positive, and carbon and oxygen, which are nonmetals, are very commonly negative to form these bonds. So one carbonate ion is going to be 1 carbon bonded to 3 oxygens. And then those will form around metal ions. Limestone and marble are almost entirely carbonates. And limestone is used in the manufacture of everyday products. We use limestone a lot in things like makeups and stuff like that. The calcite family, or calcium carbonate, is the most common carbonate material. It's usually colorless or white. It has a hardness of 3, and it has 3 perfect cleavages that meet at oblique angles. We can use acid to test to identify calcite. It will fizz up and have a reaction that forms carbon dioxide with hydrochloric acid. You'll be doing this in your mineral lab. Dolomite is another family inside of these carbonates. They're a calcium magnesium carbonate. They have a hardness of 3.5 to 4, and it cleaves into these really cool rhombohedra, these really cool kind of unique shapes that we see. You can tell the difference between it and calcite because it does not bubble when you introduce hydrochloric acid to it. So using the acid test, you have a negative reaction with the dolomites. Another group are the oxides and sulfides. Both of these contain large amounts of iron. They're not as common as our silicates or carbonates. We use them to make steel, magnets, and car parts, medicine, cosmetics, plastics, and paints. So what's the difference between an oxide and a sulfide? Well, oxide is when there's a metal element combined with oxygen. So examples are hematite and magnetite and limonite. Sulfides are when a metal element is combined with sulfur instead of the oxygen. So these are things like pyrite and chalcopyrite, which are fool's gold. Hematite is inside of these oxides and is our most common type of iron oxide. They're usually red. This sample I have here is not. It's kind of a shiny black. They can have a metallic luster. They can have an earthy luster or an uneven fracture. And they leave a very red-brown streak on a streak plate, hardness of around 5 to 6. Magnetite is a black iron oxide. It is magnetic. It's attracted to a magnet. That's one of those nice special properties we can use to test for magnetite. Lodestone is a variety of this mineral, and our very first compasses were made out of lodestone. Pyrite is an iron sulfide. It's most common of the sulfides. Its color is brassy or yellow, and its hardness is a 6. And we commonly call this one fool's gold. You're going to get a better working knowledge on all of these as we go through our mineral lab. You're going to get used to looking at charts and looking at the difference between most hardness and cleavages and streaks, and you're going to get used to testing for all of those. I hope that you've learned a whole bunch about minerals, you have a better understanding of them, and have a great rest of your day.